Well, I think we might just go ahead and start rolling along, folks. Thanks very much for coming for another one of our TESS weekly seminars. Of course, you know, TESS stands for the Center for Tropical, Environmental, and Sustainability Science here at JCU, which is in many ways one of our real foci, real dynamic groups in terms of trying to promote, especially terrestrial research, ecology, environment, paleoecology, a wide array of different kinds of things, all revolving around tropical environments. It's a real pleasure to have Julian Schrader here speaking to us today. Julian is a very diverse and well-rounded plant ecologist. He's really a plant evolutionary ecologist, and when I was going through his CV and looking at his publications, I was really struck by the diversity of different kinds of things he's done in, you know, evolution and physiology and biogeography and plant ecology and global change. I mean, there's just a lot of stuff in there, a lot of stuff to unpack. And so I'm sure Julian is very busy studying these kinds of phenomena. It's a real pleasure to have him here today. And without further ado, Julian, thanks very much.
Yeah, thanks a lot for the kind introduction. It's a real pleasure to be here, and thanks a lot, Bill, for the invitation. So I'm really happy talking to you today. And well, I tried to give you as much as a diverse background as possible today with this talk here. And so I also decided on this rather vague title on the future of islands ecosystems. So please don't expect me to tell you exactly what will happen in the future to our islands in the world, but at least I want to give you a couple of ideas how we at least can understand what may go on, or giving a bit of ideas what will happen. I selected 4 different case studies for this, and in the end try to tie them all together, and would be more than happy, of course, to also discuss this further, because I think a couple of these, everything I'm presenting today is still in progress, so not really published yet. But I'm really hoping to also get insights or stimulate future research if you are interested in joining up on these different directions I will present today. So when we think about islands, we probably most people really think of the paradise, where we go for holidays, be it Fiji or the Canary Islands for the Europeans, or the Caribbean or whatever. But there's also much more to islands. For instance, this here is Mount Teide on Tenerife. It's the biggest island in the Canaries in the Atlantic Ocean, and it has really high diversity, which you can see here already. The Teide itself, this mountain here, goes up to almost 4,000 meters, and you get a huge amount of diversity and also endemic species just found on these specific islands. And just a couple of ideas about the amazing diversity our terrestrial islands or oceanic islands support. Here on the left is Amborella. This is the only extant sister species to all other angiosperms in the world. It's endemic to the island of New Caledonia. So very special and unique species. In the middle is Lobelia from Hawaii. This is a really amazing, almost textbook radiation, where from a single ancestor, as far as we know, over 60 species radiated on the Hawaiian Islands. And on the right is an example from Australia, or rather from Australia's Lord Howe Island. This is the palms of the genus Hovea, where 2 species evolved sympatrically on the same small, tiny island. So really high endemism and a lot of really interesting plant species there. But unfortunately, as everywhere today, most of these species are also highly threatened. Just again, 3 examples. Here on the left is Berghamia insignis, also from Hawaii. And this species has last been seen about 10 years ago, and it's just known from botanical garden records. It may be extinct in the wild, we simply don't know. In the middle is a tree from a small island of Mauritius. It's just a 25-hectare island, and this is the only known occurrence of this specific tree species. If this island gets inundated or a catastrophe happening, like a fire, the species may be gone forever. Or on the right, again, an example from Australia. This is the Norfolk pine, which is endemic to Norfolk Island. Fortunately, we all like this pine a lot and plant it along our beaches, so it's not really endangered, but in its wild populations on Norfolk Island, it's just occurring in a couple of locations and has very small population sizes, also here highly endangered. So the reason why I'm bringing this up is because we simply have no idea yet about the tremendous diversity, plant diversity islands support. We don't really know how many species are there on islands globally. We have no idea about the how many species are probably endemic or unique to islands, and so on. And just to answer these seemingly very simple questions is part of the first case study, where we really want to know how many plant species worldwide are native on islands and also where, how many plant species are endemic to islands, so just occur on islands and also where. And then, of course, really important for all of us to know what is the conservation risk of these species. Are they all endangered or are they just doing fine? Yeah. And to answer this, I set out with my good colleagues from the University of Göttingen in Germany. And a couple of years back, probably 10, 15 years ago, we set up the so-called GIFT database. And it's basically a global coverage of species checklist and floras, where we know for each geographical region, as you can see in the map below, where a species occurs, and also if a species occurs on the mainland or on an island. And so far, we compiled more than 5,000 checklists and floras. And this includes almost 2,000 island regions or island entities, be it a single island, an archipelago, or a whole ocean basin, and almost 1,000 mainland regions. And this database is so far globally comprehensive. It's basically all vascular plant species so far known to science included in this database. It's about 350,000 plant species. And this database allows us for the first time to address these big questions, like how many species are there on islands? Are they native, endemic, and so forth? And just jump directly into what's interesting us most, the numbers. So the numbers I present here are based on a smaller data set of about 300,000 species. The reason is quite simple. Here we excluded species which from genera that reproduce apomictically. So these are species which are probably a bit cryptic, not really like well described yet, and heavily geographically biased. For instance, if we don't do that, England or Great Britain emerges as a global biodiversity hotspot. And this is not just because this island is so rich in species, but rather Europeans just spend a lot of time going to all these gory details and identifying all cryptic species to species level. And in the tropics, we simply haven't done this yet. So to get rid of this geographical bias, we look now at these subset of 300,000 species. And of this, 93,000 species are native to islands. So that's about 1/3 of global plant diversity. And when I represent these numbers here, we also now have the species identities for all these species. So we can really start to understand better which species are where on islands, on the mainland, and so on. And further, about 60,000 species of these are endemic to islands, which is 1/5 about of the global plant diversity. And further, 45,000 species roughly are endemic to a single island. So the previous number is just, like never occurring on a mainland, just known for islands. And the 45,000 species is really endemic to a single island, like Lord Howe, Norfolk, or Big Island on Hawaii. When we look at the taxonomy of these species, they are drawn from 17 families. We have about 477 families described so far. So 17 families of these are entirely endemic, and about 1,700 genera are entirely endemic to islands. And if you just sum that all up, plotted on the global phylogeny, like of the tree of life, we can say that about 1 billion years of unique phylogenetic history is just enshrined in these island endemics. So an incredible diversity, especially if you consider that islands just make about 6% of the global terrestrial land. So probably answering the first question, islands just contribute disproportionately to global biodiversity. And some of these islands can really be considered as a global biodiversity hotspot. But let's have a look where these islands are. Not surprisingly, if you look here at the number of natives, it's the number of natives, not endemics. And on the left, single islands. And on the right hand, like archipelago scale, like the Hawaiian Islands are an archipelago with big islands, Maui and Kauai, so on single islands within this archipelago. We see like the brighter the color and the larger the circle, the more species are there, that of course the large tropical islands have the highest diversity. At least not really surprising. Towards the poles and the smaller islanders, the less high the diversity. And the same also at archipelago level, like especially the Southeast Asian islands, New Guinea, Madagascar, the Greater Antilles in the Caribbean, they really feature most species. Well, not really surprising, I guess. But if we look at the single island, at the number of endemics, we get a slightly different pattern. Still, the large tropical islands like Madagascar, Borneo, New Guinea, maybe also New Caledonia to the same extent, support the highest numbers of single island endemic species. And also at the archipelago level, these archipelagos still also support highest diversity. Probably also not so surprising, because we know that the tropical regions also not only have high species richness, but also really high endemism at relatively small scales. Yeah, they are often old, have very complex habitats, and so on, just, like boost a really high diversity. But when we look at the proportion of the endemic species, so basically the number of native species divided by the number of endemic species, the picture changes slightly. Madagascar still emerges as a hotspot for the single island endemics. So about 80% of Madagascar's flora is endemic to Madagascar. So it's really leading the list. But also New Guinea and New Caledonia pop up as still quite diverse. And this is also, again, large tropical islands, probably detached from continents for quite a while. Well, New Guinea is basically the tropical rainforest extension of Australia. Of all the species gone extinct in Australia are now found in New Guinea, more or less, roughly speaking. But New Caledonia is an old fragment, which has these very old flora, most of which is endemic. Interestingly, though, if you look at the oceanic islands, like, again, Hawaii, here indicated by the red square, at the single island level, Hawaii is not really popping up as a hotspot of endemism. But if you look at the archipelago level, oh, well, it's a single island level, but at the archipelago level, it's really one of the highest diversities, with over 85% of proportion at the archipelago level. And this is really because most species on Hawaii, they occur on several islands, so basically decreasing the single island diversity or proportion of endemics on single islands. But at archipelago scale, basically everything is endemic there. And the same is true, for instance, like the Canaries here, or Juan Fernandez of Chile, or Tristan da Cunha in the central Atlantic. So here's really where our iconic oceanic archipelagos show their high proportions of endemism. Well, so much from the bright side. Let's look at the conservation risk of these species. And as you may have guessed, there is really something going on here. So what we did in the next step is we paired our species list for the islands with the IUCN threat status, the IUCN risk list. So all the species we could match to our islands and really see where are the IUCN assessed species distributed on the island and on the mainland. And here in the panel A, in the first bar, is the IUCN distribution for all species. So for least concern, near threatened, vulnerable, endangered, critically endangered, and extinct. You probably all know these categories. And this is what it looks kind of globally. But if you slice it up in mainland natives here in the middle, and island natives also in the middle, and island endemics on the right, we see how this picture is slightly changing. And the island endemics really have the smallest proportion of least concern, but over 50% of the island endemics are threatened, are in one of the IUCN threat categories. Yeah, it's much more than we know from the mainland. It becomes even more sobering if you look at the panel B here. Here we have the threat status on the x-axis and the proportion of island endemics in dark red, of island natives in light red, and blue of the mainland species on the y-axis. And we see here that over 50% of all known extinctions so far have been island endemics, and just about maybe 20% have been on the mainland. So islands really feature highly here on this list. And you basically see with this decreasing trend that the more endangered a plant is, the more likely perhaps it is to be an island endemic. So this is probably the sobering news. Islands are at the forefront of extinctions, or island species are at the forefront of extinctions. So we also wanted to know, are we doing enough to save our species on islands, or can we do better? For that, we used the UN 30x30 conservation target as a proxy. Perhaps you're quite familiar with this, just roughly to summarize it again. So the UN a couple of years ago agreed to protect 30% of the terrestrial land and sea by 2030. And what we did here is, for each island in our database, we pulled out, or we calculated how much a proportion is of protected area on this specific island and plotted it on our map. And you can see here is that most of the islands are at 0 or 15% protected area, so below the threshold, haven't reached yet. And just a couple of others have reached it already. if you look like which islands are protected here on the right-hand side, here we have on the y-axis the number of endemic species. Each dot is an island and the number of endemics it supports. And on the x-axis, the protected area of each specific island. And this is log transformed. So you need to keep that in mind because it looks quite well at the moment. But if we don't log transform it, it's really shocking because it tells us that about 94% of all global island endemics are occurring on islands which are not meeting the UN 30 by 30 target yet. Well, of course, the conservation target is not without critique. Some people say, well, it's area-based conservation. Yeah, we don't really know whether the island endemics occur probably just fine in the protected areas already or not. But this is the best proxy we have, at least at global scales, because we don't really know where these island endemics are distributed on the islands. And it just probably should act as awakening up for us that we need to look at our island species much better and really see, do we need to expand protected area networks and how can we safeguard our protected island species better? Yeah. So to summarize up the first case studies, well, probably quite evident, islands contribute disproportionately to global plant diversity. And many island species are also threatened. So what is next? I think, of course, a low-hanging fruit here, quite obvious, is we need to know what is driving species endemism on island. So a lot of theories have been proposed, but now we are at least in a position to test them rigorously with a large global data set. But I would like, at least for this talk, go more into the direction, how can we best protect island species under future global change scenarios? And this, of course, entails a lot of other questions, which I will try to address in the rest of the talk. We all know climate is warming. Last year has been the first on record where kind of globally we surpassed 1.5 degrees warming, and it's probably not an exception. I guess this will happen more often in the future. And we probably need to get used to this really grim forecast as presented in the last IPCC report from last year. So probably 2-3 degrees is what we should get used to. So what does it mean for our species or also on islands? Let's go back to Mount Taylor on Tenerife. What you can see here along this really nice elevation gradient, that we have a very strict and finely clustered vegetation zonation. Here in the clouds, you can't see it yet, is kind of subtropical montane rainforest, so a laurel forest, yeah? So it just occurs exactly where the border of these passat clouds is hitting. Above that, we get a belt of canary pine, so endemic pine species. This just goes as far up as probably the precipitation of the cloud sometimes reaches. So we get kind of really nice zonation here, where we get kind of 2,000 meter high elevation shrub vegetation, also with a lot of endemics for the Canary Islands. The Mount Taylor itself, we also have a couple of alpine species which just occur there. If we assume we increase temperature, ramp up temperature by 2 or 3 degrees, yeah, also the clouds would probably travel further up, the pine forest traveled further up. This will lead to high shrinkage of the shrub vegetation here, and of course, a couple of extinctions also on Mount Taylor itself, perhaps. So we will see that species are probably changing their distributions, going upwards, and probably also some species may suffer extinctions because of this, just being pushed off the top of the Mount Taylor. This is not really new. We know it already since 200-300 years that there's vegetation zonation along elevational gradient, and it comes about as each species has a specific niche requirements according also to temperature and other variables linked to elevation. And so one species niche is substituted by the next species niche and so on. That's the reason why the disease zonation of vegetation. With increasing temperature, perhaps you also see how these niches shift and probably also the communities shift along the elevation gradient. But exactly the same is also happening at global scales. And this is called the latitudinal diversity gradient, yeah, where we see at the tropics the highest diversity and also where we have the highest temperatures. And towards the poles, we basically see what we see on top of the mountains at cooler and cooler. In less diverse communities, different communities, we also see a turnover. But despite this super prevalent pattern, we have absolutely no idea how quickly species actually change along temperature gradients latitudinally. And this is the next case study where we ask how rapidly are species gained and lost when traveling along temperature gradients. So again, a relatively simple question, I would say. And this was just published last week. It's a study led by Mark Westoby, my good friend and colleague here from Macquarie University. And if you like, you can check out this paper, which came out last week in Oikos. For that, we looked at Australia. So it's an Australian case study, because I think Australia is just a perfect continent to ask how species are gained and lost along temperature gradients. The reason is, here on this map of Australia, you see the mean annual temperature. And we have a really nice gradient from the tropical north, here also in Cairns, all the way to Tasmania, where we see the temperature is decreasing, and Australia is very old, and the flora is also very old, and we can assume that all species in Australia more or less found their preferred climate niche. And this is in contrast, for instance, to my home continent, Europe, where species still travel northwards as legacy of the last glaciation. So species haven't really found their preferred climate niche yet, so they are still continuing traveling northwards. And in Australia, we probably don't have that, at least not as strongly anymore. And to that end, we got all plant records stored in the Australian Virtual Herbarium and in the Atlas of Living Australia. It's about 2.3 million plant records. And we just choose species which have at least 10 records in these big databases, which boiled it down to about 17,000 species, which are now in the analysis, which I will show you. And we basically, for each of the species, we just calculated the mean annual temperature envelope of the species. So in other words, it's just a mean and the max temperature where a species occurs in. So it gives us kind of a temperature range, a temperature niche, as you may say, of each species in Australia. And to rule out a bit of the effect of precipitation, we looked specifically at the wet eastern Australia, where we have this really nice gradient from Cape York to Tasmania. It only included records that occurred in areas with more than 700 millimeters of rain. But we got basically exactly the same patterns across all of Australia, or the dry interior, also the west coast. But we got the most, like robust patterns for the wet east. So the figures I will show you will be for this subset here. Coming straight to the results. So what you can see here is, in panel A on the left, is the species numbers on the y-axis, and the temperature, the mean annual temperature, on the x-axis. And the black line is the accumulated number of species, so the species richness for each temperature band. For instance, here for the 10-degree band, everything that is between 10 and 11 degrees, we find in Australia along the wet east coast something like 600 species. Yeah, and so this is how you can read this figure here. And we see that with temperature, also richness increases. This is really, again, the latitudinal diversity gradient. In the tropics, we have highest diversity, till it peaks here at around 20 degrees. And we'll come to this peak later. It's really interesting. And it drops again towards the really hot tropics. But this is perhaps not because the tropics don't support more species, but because in Australia, when we look at temperature bands, they also have the smallest areas. And from islands, for instance, we also know that's smaller an area, the less species support, even though probably the conditions are better for higher species diversity if we have equal area. So that's the reason why it drops here. The blue number is the species we gain with each temperature. So when we travel from the cold towards the warmer temperatures. And so here, for instance, again, between 10 degrees and the next step, we gain something like maybe 100 species. So 100 species come new, which haven't been there before. So they have basically their cold edge here. So they are added. And the red line is showing the losses. And a bit less species are lost when we travel here. We can see again, well, it's more or less even across a gradient, but this weird peak here, again, I come to that in a minute, and also the losses are always a bit lower than the gains. Again, this leads to the accumulation of species, but also more or less stable. And here's the relative species gains and losses is basically just the blue line divided by the black line and the red line divided by the black line, and it gives us kind of an average of species gain of 20% per degree and the species loss about 15% per degree. Well, let's come quickly to this weird peak, and this is exactly where the temperate or subtropical species meet up with the tropical species, roughly around Brisbane, Byron Bay area, so in the very east of Australia. And there we have these amazing national parks. You can see here, here's Mount Warning. This is a picture from the Borders Rangers National Park, where we get really, really high diversity in Australia. And also take into consideration that it also occupies the largest area, we get the highest diversity at large spatial scales in Australia in total. So really interesting. But if we go back to these numbers, and I come to my key messages here, if we have a turnover at circa 15% per degree centigrade, it means not only that we gain so many species and lose so many species when we travel from one degree to the next, but it may also be a future prediction under climate change. Yeah, it's very crude, but perhaps one of the best we have so far. And if we sum that up for, let's say, 3 degrees, what is the most likely scenario according to the latest IPCC report, we get about 25% of species gained and lost in each degree we travel northwards. And this is just, well, I was shocked when I saw this, because given enough time and we increase temperature and just wait long enough, we may see that every 4th species in our backyard, in our favorite natural reserve, national park, whatever, may be replaced by another species coming from the north. So we may see crazy amount of turnover happening everywhere in Australia. Well, what's next? I think, of course, is climate change resulting in similar turnover rates is the elephant in the room here. But I think we're not in a position yet, or don't have the data yet, to answer this. So this is really just a baseline prediction, but future will tell us if it's correct or not. But even if it's not correct or not, like as high as we see here, it will be really quite shocking to see what's happening in the future. But what we can address, and also would like to focus in the next 2 case studies, is which species are best adapted to move poleward under climate warming. So probably not all species are just, like moving exactly at the same rates, but there will be winners and losers. And of course, this is a talk about island species. I would like to go back to this. What is happening to our island species? Because on the Australian mainlands, well, we made a good job in fragmenting the Australian mainland quite a lot. So species may not travel that easily, but at least they can travel along the east coast, to track their climate niche. But on islands, and also for the endemics, there's a limit to traveling. When they reach the edge of the island, they probably can't go further, or the next suitable island is thousands, hundreds of kilometers away, or maybe not even suitable at all for them. So what is happening to those? I think this is a really pressing question, given also the first case study, there's so high diversity on islands and also endemism on islands. Here, for the next, I would like to also remain in Australia, because I think Australia is still a really nice continent for addressing these questions. And here, for instance, what you can see here is the coast of Queensland, and we have a really nice chain of islands along the east coast, or along the coast of Queensland. You see here the Great Barrier Reef Islands, or all the islands closer to the coast. You probably know some of them, and species species occur on all of these islands, but we can get an idea if we look which species occur on these islands, probably also what is their climate niche, and probably also how they colonize or go extinct on which specific islands. So do they have the capacities to travel polewards? Of course, the similar is also true for the west coast of Australia. These are the Houtmana Borealis, a really nice archipelago just off Geraldton, where we also see a really nice north-south clustering, and can try at least to track species movement polewards. And Australia is also an island nation. I was also very surprised when I plotted this figure first, but this is not the Australian continent, but these are just all the islands in Australia plotted. And you can clearly see the Australian coastline here. And there are some 8,000 islands in Australia. So it's really one of the most island-rich countries in the whole world. And these islands in Australia also more or less cover the whole climate gradient, all major climate zones, perhaps apart from the alpine meadows in the snowy mountains, Mount Kosciuszko National Parks, we can find all climate zones also there. So be it from the tropics, like these amazing islands in the Torres Strait, or of course Sandy Cays and the Great Barrier Reef, very tropical still. The wind and wave-swept islands in the Bass Strait and close to Tasmania or Victoria. There are more the dryish islands in South Australia, or the Recherche Archipelago, or the small islands of Perth. There are the Houtmana Borealis or Shark Bay Islands, which are really desert islands. The desert extends all the way to the coast. These are very low precipitation and a lot of desert species. And of course, these stunning islands up north in the Kimberleys, or the Wessel and Company Islands close to Darwin. So basically the whole breadth of Australian ecosystems can be found more or less also on Australian islands. But that's not all. Australians also have been very diligent and tedious in creating species lists for all these islands. And this is what I did in the last years. I put together a database of vegetation for Australian islands. I call this database the A-Islands database, and we're about to publish this database open access in the next couple of months. So if you're also interested in this data set, please let me know, reach out to me, but it also will be available open access, hopefully very soon. And what we did is we looked at all possible flora surveys or species vegetation surveys for the Australian islands. And so far we found nearly 850 vegetation surveys for Australian islands, from very small islands, just to a couple of square meters, up to over 4,000 islands like K'gari or the Tiwi Islands and so on, Rottnest Islands, island of Perth are included in here. And the best for me was that many of these islands, about 250, included repeated surveys. So people have been going there at least twice and recorded the vegetation, let's say 1961 and 1989 or whatever. I really recorded it. And this allows us to track temporal turnover on the islands and really seeing how vegetation on the islands changes. And in sum, this island database holds up to so far 1,350 individual species lists, more than 6,000 species. It's about 1/4 of the Australian flora, from over 135 references, and we are still growing. So we're still looking for more surveys to be included there. And you can see here that also basically all Australian islands are covered here geographically. So bluish is islands with only one survey, purple is with several surveys, and the brownish, yellowish ones are the ones where we still like to get data for in the future. And this allows us to address following questions, for instance, especially linked to temporal species turnover dynamic on islands. So, of course, one of the questions is, does species richness on islands remain stable over time? This is links to one of the most famous theories in ecology. I will come back to that in a minute. But also, what is explaining community turnover on islands? And do individual species differ in their colonization extinction rates? And if yes, why? So, and this really links to also the future scenarios for islands, because it can tell us which species are perhaps best able to track their climate niche and just pop out in new locations, and which species don't. So which species are perhaps losers if we ramp up temperature and species find themselves out of the preferred climate niche. Well, for that, very crucial, I think still a very useful theory, is MacArthur and Wilson's famous theory of island biogeography. I'm sure you're all familiar with it, but just to quickly recap it, this is a famous model, or basically the heart of the famous model, and it tells us or gives us a baseline prediction of how many species you can expect on a given island. And if we have the number of species here on the x-axis and the colonization extinction rates on the y-axis, we can basically assume, if you're starting out with an island without species, that each species migrating to an island perhaps also can establish. So our immigration rate is very high. Yeah, all niches are free, species can just go there. But as more and more species fill up on the island, also our migration rate goes down, because niches are getting filled. So it's less likely for you to establish. But as soon as we get species, of course, species can also go extinct. And the more species there are, just by chance, also more species can go extinct. So our extinction rate is also increasing with the number of species. And our extinction rate is exactly the same as our immigration rate. We reach an equilibrium, which determines the number of species an island can support. And why I'm stressing this is a point that, well, this theory gives us an idea like how many species there are on an island, but it also tells us that it's a dynamic equilibrium. So species go extinct and come again. Yeah? So islands are not diversity is not fixed in time. So species come and go, but species diversity remains the same. This is basically the beauty of this theory, which we now can test also with the Australian dataset. And for that, we just used the repeated surveys in the island database. And to this end, for this specific study, we concentrated on 150 islands, here shown in purple, which have been resurveyed. And we also get historical climate data for that. We really wanted to know how also the climate is influencing the species colonization extinction rates on the islands. So we got climate data for all surveys in this data set from the 1950s up to today. and also plant functional trait data. What we did to plant functional trait data, I will explain in a minute. Let's dive directly into the results. What we can see here on the x-axis is the years between sampling. Yeah. So if it says 10, it means that each dot, the species net change, which we have on the y-axis. So basically, it means that for this dot here, 30 species have been gained in 10 years between these two sampling periods. So an island may have been sampled in the 1960 and 1970 again, and during that time interval, it gained 10 species. Other species lost. But if you all plot it, other islands lost. If you all plot it together, we see that there's no net gain in species diversity. And this is really kind of what we would expect from the equilibrium theory of island biogeography, that despite turnover, everything else, we don't see any net change in species richness. The same also we found for the relative species net change. So if we divided the species total richness on an island with the species gained or lost, we see, well, it differs quite a lot, but basically around zero. So there was no real trend that we gained or lost in species over time. Also quite interesting, but according to the theory, is that the species composition changed. So basically the turnover, when this was our community to time X, and this is our community to time Y, they basically have the same number of species, but they only overlapped slightly. So there were new species coming into our community, but still species richness remained stable as these ones show us. But we find relatively high variation around the mean. So what's going on here? Why is it not closer to zero? This is not what is predicted by the equilibrium theory. To find out more about this, we looked at the effect of extreme weather events on species turnover rates. What you can see here again is ABC is basically our species net gains, relative species net gains, and the species composition. And these are standard effect sizes in a model that included these 6 predictor variables. So it's a species net gains in a model with the time differences included, the maximum temperature included. So the maximum temperature we could see between 2 sampling events. We got that from historical climate data. So it could indicate heat waves. We could see cold spells by the minimum temperature, and also really nice years by the maximum precipitation. So the wettest month we found in any period between 2 sampling events, but also droughts, like when we have unusually drought years in between, and maximum wind speed. So perhaps if we had a cyclone passing or really strong gales between those sampling events. And what we can see here is that maximum temperature led to a species net gain. So part of the variation we could see in the graphs before was explained by maximum temperature. Why temperature is increasing diversity, we're not sure yet, but I think because we also include many species from southern Australia, that higher temperatures, especially if they're not linked to a drought, just result in better conditions for species to grow. So we see this net increase. We see a decrease in species diversity though, with minimum precipitation, so with a drought. So species went extinct more than predicted by the theory when we had a drought, so at least in the dip in species net gains, basically losses. And on the other hand, maximum wind speeds lead to gains. And I think this is really leading because a lot of species could reach the island, but otherwise couldn't. They were propagules have been blown to the island, really leading to an enrichment of the island flora. And I also need to say these models are relatively strong, explaining up to 30–40% of the total variation we have seen in these previous graphs here. Yeah? So 40% of this variation here are explained by our models. So probably very strong evidence that extreme climate events can bring island diversity in disequilibrium, which then, if conditions are stable again over time, probably reach equilibrium again. So they are currently out of this equilibrium, either more a species than predicted by chance, and then they just come back to their equilibrium state. But we also, of course, wanted to know which species are doing this turnover, which species are gained and which species are lost. For that, we turn towards functional traits. For those not familiar with the trait concept, so it basically just morphological characteristics of a species, the link to specific species strategies. For instance, the species seeds linked to the dispersal vector and the dispersal distances, or the resources for germination. Larger seeds have more resources, for germination, and so species may have, or seedlings may have a head start over others, but also larger seeds are less likely to disperse over longer distances, so there's a trade-off. And traits we normally measure are seed mass or seed dependencies. For the leaf, they're often linked to resource acquisition or photosynthetic capacities or growth strategies, like how a plant acquires their resources. And traits we normally measure are leaf area or the leaf mass per area. And the plant height is a good proxy for dispersal distance, especially at local scales. The larger you are, the more likely that the seeds fall for longer distances away from you. But also, of course, the competitive ability. The larger you are, the better you are in shading out your competitors. And here, maximum plant height is often used. So I used these specific traits here and wanted to know, do these traits link to the colonization extinction probability of single individual species? This is what I found. So here on the x-axis, we now found the trait block transform. So the plant height first, seed mass and leaf mass per area. And here on the y-axis is the extinction probability for each single species. So each gray dot we find here is the extinction probability of a species. So it basically means a species in survey A has been present, but we revisited the island a couple of years later and it wasn't there anymore. So it was an extinction. And doing that over all islands we had data for, we found that especially smaller species were more likely to go extinct. So something like herbs and so on, they had more chance to go extinct. And when you were large, like a larger plant, like a tree, you were also less likely to go extinct. So you're more persistent. The seed mass told a relatively similar story. So if you have small seeds, you are more likely to go extinct, probably because you are really adapted to these rapid turnover dynamics. You don't really care about being persistent. You produce a lot of seed, but also go extinct. So small seeded plant species more likely, whereas large seeded species are really made for persisting somewhere. So they also had lower extinction probabilities. Leaf mass per area, which basically indexes how much resources a plant puts into their leaf tissue. So on the one hand, on the low leaf mass per area, we have something like basil, very tiny, thin leaves. And these species, which probably look a bit like basil perhaps, also are more likely to go extinct. They're not really made for the construct cheap leaves, rapidly grown, fast, like acquisition, but also probably die very quickly. There's a drought and the species will die. On the other hand, these are the species with very thick, sturdy leaves, like Banksia or some eucalypts, for instance, or Archaea, like this really typical Australian dry country species. And they're also less likely to go extinct. So these species are also made for long lasting. But surprisingly, when we look at the colonization probability, it was also those species which are large, which are less likely to colonize an island. So these are like when a species wasn't present in one survey, but was present in the next one, so it colonized an island. This gives a probability of a species to do this here on the y-axis. And here, well, if you're small, you're more likely to go extinct, but you're also more likely to remigrate. Same with seed mass. You're having smaller seeds, you're more likely to go extinct, but also, on the other hand, you reach an island faster. And the same for leaf mass per area. So these are relatively strong models explaining up to 10, 15, 20% of the variation in the trait data, and really traits linked to the colonization extinction probabilities. Well, what does it mean? If we come to the key messages, well, islands have constant and high species turnover. Communities remain at equilibrium over time, but extreme weather events can disrupt our equilibrium dynamics. And traits explain species colonization extinction probabilities. But on the other hand, it may also mean that there are specific losers and winners under future climate change scenarios. So those species, if we come back to this figure, to this figure here, those species which have high colonization probability, also those who can probably just easily bridge one island to the next and colonize new islands. Whereas other species may be losers because they may not be able to do that because they don't simply have the traits or the ecological strategies to do that. So, and extreme weather events may enforce all these problems. If we have, as predicted also by the future climate change scenarios, more likely and more frequent extreme weather events, species go extinct, so there's a disruption and new species need to colonize. But those species which probably have very low colonization probabilities are those which may lost on these islands and may not recolonize, especially if it's very frequent or rapid. So we really need to watch out these species and probably are just fine with those which have these rapid colonization extinction dynamics. They may be just fine. They may be winners of this even, but the others may be losers. So something which we definitely need to know for future conservation efforts. Well, let me piece all these now together, the 4 case studies. I think quite clear from case study 1, islands support outstanding diversity, but island vegetation is also highly imperiled by in general, like an IUCN risk categories as we've seen. Climate warming may result in high species losses, but perhaps also gains, but just of very specific species. So there may be losers and winners. And I guess for the future, for us, it's really important to assess for island species, island endemics, perhaps even more so, their extinction probabilities and also their conservation risk, and see what can we do to help them also to make it into the future. And there, of course, I'm just speculating here, transplantation of species may be a solution, maybe not, maybe more protected area, better protected area networks, in situ, ex situ conservation may be one solution, but we really need to address this. Otherwise, we may lose a lot of our really unique island flora globally, but also in Australia. Well, so much for the 4 case studies. At the last slide, I would like to make self-advertisement for a YouTube channel my wife, Connie, you see on the right, and I set up recently. And for this YouTube channel called EcoClips, we interview leading experts in ecology. We do short facts about influential theories. We also have early career features and ask about influential theories in ecology, landmark experiments, and so on. And so far, we have a couple of interviews already. Next week, I'll be coming up to Cairns myself with Connie. We will interview Bill. He will talk about tropical diversity and conservation. And if you like this idea, feel free to check it out. This QR code will lead you to this YouTube website. It's non-commercial, free. We don't earn any money with this. We really want to use it also for teaching, outreach, science communication, and so on. And it would be great if you could pass on the word, spread the word, subscribe to the channel, support us if you like it. Yeah, with this coming to an end, I'd like to thank you very much for your attention and for having me here today. So probably we have still time for discussion, I think. And maybe, Noel, if you have a question, please go ahead.
Okay, since the MC is not there. Yeah, Julian, thanks very much for the talk. It was really interesting. I've been working on flying foxes, mostly focused on the spectacle flying fox in the wet tropics of far north Queensland, but also looking at flying foxes and their behaviour and roles across their range, really. And I came across this very interesting paper where the flying foxes on islands in the Tonga region have declined to such a point that they're now considered functionally extinct. And while you were talking, I was wondering if you had considered the role of certain fruit distributors in the survival or extinction of various species. Flying foxes, carry huge numbers of figs and myrtaceous plants and so on. And their functional extinction could cause co-extinctions of certain species of plants as well. Can you comment on that, please?
Yeah, definitely. Yeah, that's a really interesting point. And I would say also in Australia, we find this, for instance, up north in Cairns and so on, we have these Ducula bicolor species which fly to the islands and probably for roosting overnight and also bring a lot of seeds and so on. And well, for the global study, we haven't integrated dispersal modes yet. Yeah, it's just too many species, but we're working on this. We would like to add traits on that, but that probably needs a couple of years still till we come to conclusions whether our island endemics also have specific dispersal modes and so on. But from field studies, which I did in New Guinea, so tropical systems, but also in the Houtman-Abrolhos archipelago in Western Australia, I found that species dispersal mode acts as a really strong filter for species or plant species which you can find on the islands. In New Guinea, most of the species were bird dispersed, and here the size or the type of the bird or bat dispersers played a big role. So For instance, also a lot of ducola species were in this New Guinea archipelago, and these only like the larger islands, and they eat at larger seeds. And so I got a really strong link between where these ducola species go and where I find the large seeded plant species. Yeah, they're really, really strong links. On the other hand, tiny flower peckers or so on, they were rather going to the smaller islands, and they were also where the smaller seeded species were. So there's a really, really strong link between the dispersers and which species occur where. And I guess, having said that, I haven't studied this myself, but I know about these studies from Tonga you mentioned. There's also a couple of other examples around the world that plant species are probably, or we're building up a huge extinction depth in plant species by eliminating their dispersers. And probably we'll see this also coming up more and more in the future. So I guess, yeah, just guessing here, that are probably also are endemics to some extent, but those species which are losers are probably also those who have very specific dispersal agents, yeah, be it bat dispersal, with bats going extinct, or other vectors which just make it really hard for species to go from one island to the next.
Very good. Any other online questions?
Yeah, Bill, it's Penny here. How are you?
Penny, yeah, good. Man.
I've been lately researching Malaysia, and there 90% of 90% of modern bird extinctions are on islands, and including in Malaysia. And there's been some research showing that up to a third of vegetation on certain islands is affected by those island endemics. So there is a little bit of research out there on that sort of thing. But what I wondered was, when you were looking at your Australian islands, how you were taking into account the fact that they are, that not that long ago, I suppose, 8,000 years, they were not islands. So as part of the continental shelf, compared, for instance, to those islands in eastern Indonesia, which are all oceanic and have a different sort of dynamic.
Yeah, definitely. I should have made that perhaps clearer in the talk, but with these two data sets, the global one and the Australian one, we're really talking about more or less different island types. Yeah. So in the global one, we really have also the oceanic islands. And in Australia, on purpose, I only focused on the continental islands. As you said, all these islands have been connected to the mainland quite recently, probably 10,000 years ago. There's not a single endemic species on any of the islands I have in the Australian database, also on purpose, because I was really interested in seeing these meta-population dynamics, yeah, really seeing which species colonize which islands, how fast, where do they come from. We also have a couple of studies, I haven't shown them today, where we look at these mainland source pools and what is acting as a filter for species colonizing from the mainland to these islands and so on. So these completely different dynamics. And also, even within sometimes 10, 20 years, some of the smaller islands had 100% community turnover. So we couldn't find a single species, which was at 10 years before again. So these species are really, like rapidly doing turnover. But this allows us to get an idea about winners and losers and turnover rates at ecological timescales. And we definitely have no means to really, get a good data set together to look at evolutionary timescales. It's just, beyond our grasp. So I'm using the Australian data set to get an idea about the magnitude of these changes and perhaps also linking traits to these changes. But all islands or all species in Australia on the Australian islands also occur on the mainland. If we lose them on the island, they're not lost altogether. We still have on the mainland, but of course it's concerning because island population also make up perhaps of some, or at least Pisonia, for instance, a large share of their population.
Very good. Okay, we just have a question here. Sorry.
Hi, Julian. I can tell you how much I like your talk, maybe because I'm a plant ecologist too, and it's just so cool to see, this large scale biogeographical studies you're doing. Congratulations. It really is very exciting. I also work on invasive plants, and I assume when you were mentioning at the beginning plants native to islands and plants native to the continent, some of these plants will be the same species, right? That they're native to both, right? Okay. But then, do you have any information about non-native to Australia species, and is there any pattern that is arising from there? Or? And you would you like to do this, like a summary of that, or is that like too big and another presentation?
Well, yeah, thanks for this question, of course. It's very, very, very important as well. Well, I could give another presentation on that, of course, but just do a brief, like what we found is that invasive species or naturalized species in Australia are picking up over time. If we plot like from the 1950s, where we have data from up to today, we really see a linear increase in the number of natives making up the flora of the number of naturalized species making up the flora of the island. So they increase in numbers. I haven't really found a strong link yet in the models that numbers of invasives lead also to extinctions on the islands. It's probably just a matter of time. Also, my data set is present absence. So if one species native is just like hanging on with a couple of individuals, it's still present on the island, but probably the population decreases. It would be amazing to see population dynamics and perhaps link increase of invasive or naturalized species to declines in population size of native species. Haven't done this yet. I don't know much about this yet. Yeah, but we see invasive species becoming a problem, and also most of these islands in Australia, in my data set, are really not affected by humans. So they're just like islands off the coast, and naturalized species, they come there naturally. So they disperse also there. So they just become part of the flora. They're just not aided dispersal by us, but they just they just come there and compete with the natives, and often just do better. So this is probably also leading to a lot of turnover in the future, and maybe also population declines, or maybe even local extinctions of native species.
Well, all the modeling suggests that invasives should expand their distribution, especially here from the tropics. They're predicted to go way farther south, probably more than the natives even. So that I'm not sure if you have a database that would be useful to test some of those hypotheses, but I invite you to explore that. It will be very interesting. This links me to another thing. Sorry, a very big question. When you were talking about a specific leaf mass area, there's something about this thing of plants with higher specific leaf mass area having a lower probability of extinction that somehow kind of strikes me as there may be another hidden variable in there. And just, I'm throwing that out there. I don't have any information right now, but you think there could be like maybe a phylogenetical bias, like maybe older lineages have higher leaf mass areas and they have some kind of relictual distribution, and they might be less prone to extinction because they've been just there for longer or something like that?
Yeah.
Maybe it's a weird idea, but it just strikes me as something that I will expect lower leaf mass area to survive more.
No, so let me perhaps explain again. So larger leaf mass per area, for those not familiar with this trait, means you have more weight per specific area. So if you assume a square centimeters of area leaf, higher leaf mass per area means that you have a thicker, like more expensive leaf, like really if you assume a Banksia, for instance, on the extreme spectrum. And there is no phylogenetic bias in my analysis because all the species on the islands, they have colonized there. So regardless of lineage, everybody had to go there. Yeah. So it's not that an island has been colonized by Banksia from the beginning and they just cling on because they have been there for the last million years. Yeah. This is not the case. They also moved there. We know that more or less. Yeah. From the dynamics and sea levels on the islands. I think what we see here is that if you just assume a Banksia, because I think most Australians are familiar with these genus, these are species which are very slow growing and they're really well adapted to also, like last through a drought to very unfavorable conditions. And other species with very flimsy, cheap leaves, they may just, like be fine in a good year, but as soon as a drought strikes, our local basilicum, they will just wither, it will just go extinct. On the other side, of the low leaf mass per area spectrum. And these species, like the Banksias with a high leaf mass per area, they're just better, in my opinion, or this is my interpretation, to hang on. But a Banksia, also once extinct, has very low chances to remigrate. So there's a trade-off. You can't do everything best, So either you cling on and try to persist, But once you go extinct, you have less chances, or you don't care to go extinct because you can easily remigrate. And this is these two spectra which we see quite clearly in the data. And it has been speculated that it will be like this, but never shown for islands. I think the data really supports it. But well, it's correlative data. It doesn't 100% tell us the mechanisms, but I think there's a strong link or hint at least in this direction.
And it's not driven by just a few species, like you have a lot of species across.
Yeah,
that.
these are several hundred species. Yeah, so these data clouds I've shown, I think 500-600 species are underlying there. Not just Banksia, but across all genera.
A lot to keep the conversation, but the mic is being pulled from me. Thanks for it.
Yeah.
You can't really do a separate symposium if you want. Is there any last questions before we close things up? Okay.
Hi, Julian.
Big thanks.
Sorry.
Oh, sorry. Is there an online question? Yeah, go ahead.
It's James here. I was just wondering, what sort of spatial and temporal standardization did you use for your repeated surveys?
Yeah. So quick answer to that. So I included a species list which have been surveyed from the 1950s up to 2020. Yeah, I included those lists because we have historical climate data for that, reaching back to 1959. There's the best historical climate data out there available at a monthly basis. So that's the reason like how we limited to this last 7 decades. And spatially, all of Australia. So I have islands from just off Cairns all the way to Tasmania, to Perth, to the Otman Abrolhos. So basically all of Australia is included in there, 150 islands. And maybe just quickly, these two data sets, a global data set of all plant species worldwide on islands in the mainland, as well as the Australian ones, are made open access, and I'm more than happy also to share this or collaborate. So if anybody's interested in this, just let me know. Yeah, this is not hidden data, it's out there, or it will be soon out there.
Very good.
Cool, thank you.
All right, great. Okay, well, thank you very much, Julian. That was a really interesting seminar. Lots of good stuff packed in there. So really appreciate it. And on behalf of everyone, thanks very much. Appreciate it.
Yeah, thanks a lot.